Here's our third lesson in the logarithms unit. It's on the product and quotient laws of logarithms. I'm going to start by giving you the proof of what the product law of logarithms is. Then I'll just give you the quotient law, and we'll do some questions that use those two laws. So the first step in our proof, I've given you two logarithmic equations, x equals log base b of m and y equals log base b of n. I want you to rewrite each of those equations in exponential form. So the first one, let's rewrite that equation in exponential form. Well, remember, a logarithm finds you the exponent that goes on the base to get the argument. So it's telling us x is the exponent that goes on b to get m. So that's how we write it in exponential form. b to the power of x equals m. And I'll do the same thing for this logarithmic equation. I'll rewrite that in exponential form. It would be b to the power of y equals n. Now, because I'm going to prove the product rule to you, I'm now going to write the product of those two powers. So b to the x and b to the y, and I know that would be equal to m times n because that's what the powers are equal to. So in my proof, I'm going to say b to the x times b to the y must be equal to m times n. And that must be true because b to the x is equal to m and b to the y is equal to n. And now on the left-hand side, I have two powers being multiplied, where the bases of those powers are the same. That's very important. We can now use the exponent rule that tells us to keep that base and add the exponents. And I'm now going to convert this into a logarithmic equation. When I write this in logarithmic form, I would have log base b, right, the base of the power goes there, of m n equals the exponent on the power x plus y. This equation means the exact same thing as that. The logarithmic equation tells us that x plus y is the exponent that goes on b to get m times n. And that's exactly what this equation says. And then my last step in my proof is going to be replacing x and y with what we said they were equal to at the very beginning. X is equal to log base b of m. So I can replace that x with log base b of m. And I can replace the y with log base b of n. And this is our product rule of logarithms. If we have two logarithms that have the same base, that's very important, that are being added, I can express those as a single logarithm by keeping that same base and multiplying the arguments. So that's what we call the product rule of logarithms. And if you have a good understanding of exponent rules back from grade 9, you could probably guess what we would do if, instead of the logs with the same base being added, what if the logs with the same base were being subtracted? If you know exponent rule as well, we could have done a proof for this and figured out that we actually could express these two as a single logarithm by keeping the same base and dividing the arguments. So these are our two rules we're going to work with today. Here's the product rule, and here's the quotient rule. It's important that you notice in order to use these rules, the bases of the logs that are being added or subtracted have to be the same. All right, on this page is a summary of now everything we know about logarithms. And these are all of the rules we're going to need to know for the rest of the unit. Feel free to pause the video now and look through them carefully, but I'm just going to briefly remind you of all the things we've learned. So we learned power law of logarithms. If the argument of our logarithm has an exponent, we can rewrite that as exponent as the coefficient of the log. That's why it's here. And then we just talked about product and quotient law of logs. If we have two logs with the same base being added, we can write it as a single log, keeping that same base and multiplying the arguments. If we have two logs with the same base being subtracted, we can write it as a single log, keeping that same base and dividing the arguments. We looked at the change of base formula in last lesson. If we have log base b of m, we can rewrite that as a quotient of two logarithms. If we make the log in the numerator have that as the argument, and the log in the denominator has that as the argument. And in this quotient of logarithms, this formula has the basis of these logs being 10, but they could be anything. It doesn't matter as long as they're the same. And then we've been working with these next two a lot, changing from an exponential equation to an equivalent logarithmic equation, and vice versa, going from a logarithmic equation to an exponential equation. So you need to be able to confidently move between those two versions of a formula. And then here's some other helpful tips down here. If we have log base a of a to the b, the answer is just b. Know that if you don't see a base on a log, the base is 10. We call that the common logarithm. And log base b of b is 1. Why is that? Well, remember, a logarithm just wants to know what exponent do you put on the base to get the argument. So what exponent can you put on b to get b? 1. All right, let's get into some examples. The question says, write as a single logarithm. I see 3 logarithms being added and subtracted, and all 3 logarithms have the exact same base. They are all base 5. Because they're all the same base, we can use our product and quotient laws to combine these. So let's just look at the first 2 logarithms right now. Those first 2 logarithms are being added and they have the same base, so I can combine those two as a single log by keeping the base the same and multiplying their arguments, 6 times 8. And 6 times 8 is 48. And now I have 2 logarithms being subtracted, and those logarithms have the same base, which means I can rewrite them as a single logarithm with that same base, with the arguments being divided. So the argument becomes 48 divided by 16. And 48 divided by 16 is 3. So I have log base 5 of 3. And there we have it. We've rewritten those 3 logs as a simplified single logarithm. The next one, part B. I have 4 logarithms being added and subtracted. And all of those logs are base 10. I don't see a base on any of them, so they're all the common logarithm, which means base 10. Before I start doing the product and quotient rules to combine these, it may make the question easier, and in fact it definitely will. It'll make it easier if we look for like terms that can be collected. So how do we find like terms when dealing with logarithms? When dealing with normal terms, like let's say we had 3x squared and 5x cubed, we could not collect those together because they're not like terms, because the variables have different exponents. So when we talk about like terms in the past, we're talking about terms that have the same variable and the same exponent, like 3x squared plus 5x squared. We could collect those together, and when we do that, we just add the coefficients, and we keep the x squared the way it was. So how can we apply that to logarithms? Well, for logarithmic terms to be like terms, the logarithm has to have the same base and the same argument. So for example, this positive log y and negative log y, they both have base 10 and their arguments are both y. So the bases are exactly the same and the arguments are exactly the same. So we could collect them like terms just by adding their coefficients. So 1 plus negative 1 is 0, right? Log y minus log y is 0. Those are gone. And if you wanted to try and use log rules to do this, I mean, we could, right? Log y minus log y, 2 logs being subtracted with the same base. I'll just do it off to the side. We could write it as a single log, keeping the same base and dividing the arguments. Y divided by y is 1. And then remember, what does this logarithm mean? It means what exponent goes on 10 to get 1? Well, 10 to the 0 is 1. Therefore, the answer to this is 0. So that's just showing you that using log rules would still work. It's just a waste of time when they're like terms. We can just collect them together. 1 log y minus 1 log y is 0 log y. So those are gone. Now all I have left is log x plus log 3x. Now those are not like terms because the arguments are different. They do have the same base though, so I could use the product rule to write them as a single log, keeping the same base and multiplying the arguments. So I need to do x times 3x, and that would be 3x squared. And that's as simple as I can make this. Now, a common mistake, people want to try and bring this exponent to the front, but we are not allowed to do that in this example because this 2 is not an exponent of the entire argument. It's just an exponent of the x, not the 3. You can only bring the exponent down if it's an exponent on the entire argument. So that's as simple as we can make this one. Part C, this is a great example because we're using the change of base formula, but kind of in reverse. So remember, the change of base formula told us that if we had log base b of m, that would equal log m over log b. And the version of the formula I always give you is like this, where the bases of those logs in the quotient are 10. That's why we don't write them. But they don't have to be 10. They can be anything. In fact, they could be 2. All that matters is that they're the same number. So these could both be 2. So we could use this version of the change of base formula and then go from the right side of this equation to the left side. If I do that, I could rewrite this as a log base 5 of 7. Let me just show you in a calculator that what I've done is equivalent. So in the question, it was log base 2 of 7 divided by log base 2 of 5, which is equal to this. And I've said that's equal to log base 5 of 7. And it is. And let me just prove to you that it doesn't matter what the base of those two logs are. All that matters is that they are the same number. So this is also equal to log 7 divided by log 5, using just the common logarithm that has base 10. Same thing. Or log base 25 of 7 divided by log base 25 of 5. Same thing. All of those are equivalent to each other. So that's how we would rewrite those two logarithms as a single logarithm using the change of base formula. Part D, this one's a little different because if we look back at the product law of logarithms, what's the coefficient of the logs being added? Both 1. And same when they're being subtracted, what are the coefficients? They're both 1. So in order to use the product and quotient law of logarithms, the coefficients of the logs have to be 1. And if we look at part D, they're not. This one is 3 and this one is 2. So what do? We use the power law of logarithms, which tells us we are allowed to rewrite the coefficient of a log as the exponent on the argument. So I'm going to do that with both of those coefficients, which will give me log of 12 minus log of 2 cubed plus log of 3 squared. And then I'll simplify each of those arguments. 2 cubed is 8, and 3 squared is 9. And now I'll combine the first two logarithms. They are logs with the same base being subtracted, so I could write them as a single log with their arguments being divided. And now I have two logs being added that have the same base, so I can write them as a single log with their arguments being multiplied. So I would have 12 times 9 over 8. And then we should simplify that argument. Well, I know 12 over 8, 4 goes into both of those, into 12 3 times, into 8 twice. So I would have log of 3 times 9 is 27 over 2. So there's my simplified single logarithm. Example 2, it's the same as example 1, except for it says after you write it as a single logarithm, let's evaluate it. So part A, two logs being added, and those logarithms have the same base. So we can rewrite those logarithms as a single logarithm, keeping that same base with the arguments 4 and 16 being multiplied. And 4 times 16 is 64, so I have log base 8 of 64. And then to evaluate this, don't just blindly turn to your calculator. Remember, what does this mean? It means what exponent goes on 8 to give us 64? Well, 8 squared is 64, so the answer to this is 2. Let's try another one. I have two logs being subtracted, where those logarithms have the same base, so I could rewrite those as a single logarithm, keeping that same base with the arguments being divided. And 405 divided by 5 is 81, so I have log base 3 of 81. And now we're looking for what exponent goes on 3 to make 81. And that answer is 4. And if you weren't sure about that, you could ask your calculator in one of two ways. If your calculator has a change of base button, you could simply type log base 3 of 81. If your calculator doesn't have a change of base button, you use the change of base formula, which would be log 81 divided by log 3. That's also 4, same thing. And why is the answer 4? Because 3 to the 4 is 81. A logarithm is just a way of asking what exponent goes on the base to get the arguments. We figured out 4 is the exponent that goes on 3 to get 81, and that just verifies it. Part C, once again, these logarithms, their coefficients are not 1. So before I use the product rule, I'm going to have to rewrite those coefficients as the exponents on the argument. So this would give me log of 5 squared plus log of 16 to the half. Well, remember, an exponent of a half just means square root. So I have log 25 plus log of 4. And now notice these logarithms are being added and both logs have base 10. So I could rewrite them as a single logarithm with their arguments 25 and 4 being multiplied. And 25 times 4 is 100. And remember, this common logarithm does have a base of 10 even though I'm not writing it. So what this expression means, it means what exponent goes on 10 to get 100. Well, 10 squared is 100, so my answer is 2. Example 3 says write the logarithm as a sum or difference of logarithms. Okay, so we're working backwards this time. These are single logarithms, and we'll use our product and quotient rules to write them as a sum or difference of logs. Part A, notice the argument of the logarithm have two factors being multiplied together. So I could rewrite those as a sum of two logs that have that same base of 3. The first one will have argument x plus log base 3 of y. Part B, well, this one I don't have the argument as a product or quotient of anything, so it may help if I start off by rewriting that 20 10 times 2. And now that I notice that the argument is a product of two things, I could write those as two logarithms if I add those two logarithms and put each of the factors as the argument of those logs. So log 10 plus log 2. Oh, and log 10? Well, that just means what exponent goes on 10 to get 10? That's 1. Log 10 is just 1, so 1 plus log 2. There we go, there's an answer for part B. And that's not the only answer. We could have had log 4 plus log 5, for example. Part C, the argument is a product of A, B squared, and C. So I could write this as a sum of 3 logarithms. Of log A, of log B squared, and of log C. And then a final answer for it to be fully simplified, if your argument has an exponent on it that's not 1, for example this 2, we should use the power law and write it as the coefficient of the log. So my final simplified answer should be log A plus 2 log B plus log C. Example 4 says simplify the following expressions. So for an expression to be fully simplified, the argument should be as simple as possible. So let's simplify root x divided by x squared using our exponent laws. Remember that root x is really just x to the half. And now in the argument, I have two powers of x being divided. So if you know your exponent law as well, we could write that as a single power of x if we subtract the exponents. 1/2 minus 2. So with the common denominator, that'd be 1 over 2 minus 4 over 2. That's negative 3 over 2. And like I was saying before, for an expression to be fully simplified, if your argument has an exponent, we should use the power rule and rewrite that exponent as the coefficient of the log. So I would have negative 3 over 2 log x. B, I've got 3 terms here. I need to write this in as simplified form as possible. So if there are any laws I can use to combine these terms, I want to do that. Well, notice all 3 logarithms are all the common logarithm, meaning they're all base 10 logarithms. So I can use the product and quotient laws. The first 2 logs are being added, so I could write those as a single logarithm by multiplying their arguments. And this square root of x cubed, that's the same as x to the 3 over 2. And that needs to be multiplied by x squared. And I'll deal with this log of root x. I'll write that as x to the half. So this first logarithm I wrote, I could multiply these powers of x together by adding their exponents. 3 over 2 plus 4 over 2 is 7 over 2. So I have x to the 7 over 2 minus log of x to the half. And now these logs are being subtracted. So what I can do is divide their arguments. X to the 7 over 2 divided by x to the 1 over 2. And when powers of x are being divided, I can write them as a single power by subtracting their exponents. 7 over 2 minus 1 over 2 is 6 over 2, which is 3. And then I can bring that exponent of 3 on the argument, write it as the coefficient, 3 log of x. Now there's another way to do this question, and maybe it's actually an easier way. I'll show you, and then you can decide which way you would like better. But I'll just show you that it is in fact going to get us the same answer. So I'll just shrink that method, put it off to the side so we remember what we did. Instead of doing that, what we could have done instead, I noticed that if I took the exponents of the arguments right away and wrote them as the coefficients of the logs, I'd have a bunch of like terms that I could collect. Let me show you what I mean. Well, remember this log of root x to the 3, that's really just a log of x to the 3 over 2. And we have log of x squared and minus a log of x to the half. If I take all of these exponents and write them as the coefficients, each log then has a base of 10 and an argument of x. They all have the same base and same argument. Let me show you. See how they're all like terms? They're all base 10 logs, and the arguments are all exactly the same. They're all just x. So what we can do with that is collect them like terms. Just add their coefficients. 3 over 2 plus 2. Well, let me help you out here. Let me rewrite 2 as a fraction with a denominator of 2. So that'd be 4 over 2. There we go. So 3 over 2 plus 4 over 2, that's 7 over 2. Minus 1 over 2 is 6 over 2, which is just 3. So we have 3 log of x. There we go. Same answer, just a different way of approaching the question. And our last example. I have two logs being subtracted, and they're both base 10 logs. So I can write them as a single log with their arguments being divided. And now I need to simplify that argument. And if I look at the numerator and the denominator, both of those could be factored. The numerator I could common factor out at 2, and the denominator is a difference of squares. I could rewrite that as x minus 1, x plus 1. And then notice those factors of x minus 1 cancel out, and this is now equal to log of 2 over x plus 1. And that's the end of our lesson for product and quotient law of logarithms. Make sure you practice all of the questions in the homework that goes along with this. Being comfortable with these rules is really going to help you as we finish the unit by solving exponential and logarithmic equations.